A tutorial on phasors. We begin with the topic that was before phasors, RMS, root mean square value, and effective value, with one question, this one. What is the RMS value of this current? What current is that? It is a periodic current, a current with a period of 2 seconds. That is 0 during the second half of the period, and it's a parabola 10t squared from 0 to 1 that climbs up from 0 all the way up to 10 amps. Let's find what that is. Root mean square. We take the square root of the average of the square of that current. So we take the square root, 1 divided by the period 2, and the integral between 0 and 1, because from 1 to 2 the integral is 0, of 10t squared, and all of that squared. Well, I don't really feel like doing integrals right now, so I will use the HP50G. This way, I write that, making sure that t is the independent variable here at the top. And then press the key evaluate, and we get that the RMS value of that current is root 10 amps. That is the answer to that question. Let's move on. Phasors and Op Amps. This is an exercise taken from the textbook by Alexander and Sadiku, 4th edition, 1167, page 498. This exercise. We have a sinusoidal source feeding an amplifier and a 12-ohm resistor as a load. And the questions? The question is find the active and the reactive power delivered by the source. And secondly, find the average power in the 12-ohm resistor, the load. The first step is finding what is omega, the angular frequency from the source, 2 radians per second. And with that omega, we can replace the inductance by an impedance, J omega L. That would be J 2 radians per second times 1.5 henries. That is J 3 ohms. And that value will replace the inductance in our diagram. We do something similar with the capacitor. Instead of 0.1 farads, we're going to write negative J1 over omega C. Omega again is 2 radians per second, and C is 0.1 farads. Negative J5 ohms, that will replace the value of that capacitance. What about that source? How are we going to represent that source? Well, 0.6 volts is the peak value of that source. We are using IEEE phasors, in which the value we use is the RMS value of the sinusoid, 0.6 divided by root 2. 0.6 divided with root 2 with a phase of 20 degrees. We are ready. Let me copy that circuit, and then we apply M&A or any other method of solution to the circuit. Here is the circuit where we have replaced the sinusoidal source with a phasor, the inductance by an impedance, and the capacitance also by an impedance. We are ready. We need to find V0, because with V0 we will be able to compute what is the power in the 12-ohm resistor, the load resistor. How do we do that? Well, this is merely an inverting amplifier like the ones we saw in EEC 251, and we know what is the gain of such an amplifier. It is just negative R2 over R1. You say, wait a second. But in this case, it's no R2 and R1. We have an impedance in the place of R2, and we have another impedance, 4 plus J3, in the place of R1. Fine, we use impedances. Negative Z2, which is the parallel of negative J5 and 10 ohms, divided by Z01, which is 4 plus J3. And that multiplies the input voltage as a phasor, 0.6 divided root 2 with 20 degrees. Do the math, and that is V0. the voltage and the load, 0.38 volts with 99.7 degrees. 0.38 volts is the RMS value of the output voltage. And we'll remember that if we square the RMS value of the voltage in a resistor and divide that by R, we get the power in that resistor. Yes, the power in the 12 ohm resistor is 0.38 squared divided by 12 milliwatts. That answers the question, what is the active power in the load? But there was another question. What is the power in the source, in this source on the left? If we know the current in the source isobus, of course computing the power of that source would be a matter of multiplying the voltage by the complex conjugate of that current isobus. How do we compute that current isobus? Observe that in this amplifier there is negative feedback. You see that impedance connecting the output of the amplifier with the inverting input. There is negative feedback. That means that Vn is equal to Vp. But Vp is 0 volts because there is a connection to the reference node. That means that Vn is also 0 volts up there. So that current Is is just the voltage of the source minus 0 divided by the impedance plus 4 plus J3. That is 85 milliamps with negative 17 degrees. And we can compute the power in the source as voltage in the source by the conjugate of that current, like so. The power in the source is 28.8 milliwatts active power and 21.6 millivars reactive power delivered as well. That completes that question. Let's move on. More phasors and more amps because it's so important. This circuit looks a little bit like the previous one, but in this case Z2 is a series RL circuit. Well, it's an exercise also from the Alexander and Sadiku 4th edition, problem 1166, page 498. The question is, what is the active power in the 6 kilo ohm load resistor in that one? If we know the current through that resistor, it would be a matter of using 6 IRMS squared to find the power there, right? The active power. To compute that current, it would be nice knowing this voltage V0 over here. Divide V0 by the total impedance in that branch, we have the current. Fine. How do we find that V0? Well, we solve the amplifier. And that amplifier is an amplifier that is in the configuration that we have seen in 251. Observe, I am assuming that the phasor given for the voltage source is an IEEE phasor. That 2 is the RMS value of that voltage. This one is also an inverting amplifier, so we know that the voltage gain is going to be negative Z2 over Z1, and there is a typo there, right? Z2 over Z1. That is negative 2 kilos plus J4 kilos divided by 4 kilos plus J3 kilos, and that multiplies the input voltage 2 volts with 45 degrees, and that's how we obtain that the output voltage V0 over here should be 1.8 volts with negative 108 degrees. What is the current in the 6 kilo ohm resistor? Divide that voltage V0 by the impedance of the load, 6K minus J2 kilo ohms. That current is 283 microamps with negative 90 degrees. Why did we want that? Oh, so we could square the RMS value of that current, 283 microamps, and multiply that times 6 kilo ohms, the resistor. That's how we find that the active power in that 6 kilo ohm load resistor is 480 microwatts. And that is that. Let's talk a little bit about phasors and wattmeters that we have seen in this class. A voltmeter has two terminals, right? A black one and a red one. An ammeter also has two terminals, a black one and a red one. Well, a wattmeter is a combination of a voltmeter and an ammeter, as we saw in class, and we saw that in 251 as well. A wattmeter measures one voltage and one current, and then it multiplies them and finds the average of that product. A wattmeter has four terminals, right? It has two terminals to measure a voltage. They should have been red and black, but no, not really. They are positive and negative, or they have some other kind of notation in them. And it has another two terminals to measure a current. They are neither red and black. They are more often plus and minus. The wattmeter multiplies the voltage and the current and finds the average of that product over one cycle of the voltage. A wattmeter measures active power P. That's correct. The symbol of a wattmeter is something like this. You see, it has a current coil through which the current in the load will flow, and it has a potential coil that will be serving as a voltmeter across the load. If the wattmeter is ideal, which is our assumption in the following exercises, the voltage drop across the current coil is 0. So it behaves as an ideal ammeter, and the current through the potential coil is 0 amps. So the potential coil has an infinite impedance. It's an ideal voltmeter as well. We can represent the wattmeter this way too. The voltage drop across the ammeter part of the wattmeter is 0, and the current through the voltmeter part is 0 amps. Ideal one. By the way, tutorial time. The wattmeter reads 1.5 kilowatts. The ammeter on the right is reading 9.6 amps RMS. The question is, what is the power factor of this load? Well, you have the voltage, right? 240 volts RMS, which is given by the source on the left. You multiply the voltage times the current, and you get the apparent power of the load. You divide the actual wattmeter reading, the active power P, 1500 watts, by the apparent power, and that is the power factor of the load. More about wattmeters now, an exercise taken from Alexander and Sadiku, 4th edition, 1179, page 499. We will consider that wattmeter to be ideal, so there is no voltage drop across the ammeter part of the wattmeter, and there is no current flowing through the voltmeter part of that wattmeter. In other words, it is as if that wattmeter was not there. The question is, what is the reading of that wattmeter in that circuit? Oh, well, first of all, we're going to find what is omega in that circuit from the source, 100 radians per second. And we'll use that value to represent the inductance 10 millihenries as an impedance, J10 ohms, and the capacitance by another impedance, negative J20 ohms. We are ready. The voltage source will be represented by a phasor. RMS value 0 degrees, 10 over root 2, 0 degrees. The circuit looks like that. J10 ohms here, negative 20 ohms, J over here, and 10 over root 2 volts. We solve that circuit. Remember, the ideal wattmeter actually is invisible in that circuit. Well, we'll choose a reference and node 1 and node 2. And a direction for the current in the 40 ohm resistor in this reactor, and over here I0 is given, so I will not touch it. We begin writing equation, a CTL equation, a control equation first. I0 is V1 minus V2 over 20, right? right? And now we write a KCL equation for node 1. This voltage of the source, 10 over root 2 minus V1, because the wattmeter has no voltage drop in it, divided by 40 ohms. That current going into node 1 is equal to 2I0 going downwards, plus V1 minus V2 over J10, plus I0. Fine. One more equation, the KCL equation for node 2. V1 minus V2 divided by J10, plus the current I0 that comes from the top, that is equal to V2 divided by negative J20. We have three equations, three unknowns, V1, V2, and I0. We solve them, and we get that V1 is root 2 with negative 90 degrees. Those are volts. Okay, so we have that voltage there, which is the voltage seen by the wattmeter. We only need the current that goes through the wattmeter now. That current happens to be given by this computation. 10 over root 2 minus V1 over 40, and now we know V1. We can compute that current as 0.180 with 1131 degrees. That is the current in the wattmeter, and we know V1 is the voltage in the wattmeter. So the average is P, the active power, is the RMS value of the voltage root 2 times the RMS value of the current 0.180 times the cosine of the angle of the voltage minus the angle of the current, negative 90 minus 1131, that is negative 50 milliwatts. That means that in reality the circuit on the right is delivering 50 milliwatts of power to the circuit on the left. And that is the reading of that wattmeter, negative 50 milliwatts. Now let's visit another exercise, one on Phasors and Thevenin. This one, Thevenin? Yes, that's right. The question is, what is the maximum power that can be absorbed by the impedance ZL or ZL? And what should be the value of that ZL for maximum power absorption? Actually, 2 should be the first one and 1 should be the second one, but that is the way they came out in the book. For maximum power, we know that in AC steady state, the external impedance ZL has to be the complex conjugate of the Thevenin impedance of the rest of the circuit. That's right. So you make the external impedance the complex conjugate of the Thevenin impedance of the circuit. That means that we need to find the Thevenin impedance at that port where ZL is currently connected to. The first task is remove that impedance there. Leave the port open to find the Z Thevenin, the Z Thevenin. Well, all sources in that circuit are independent, so we can use the kill the sources method to find Z Thevenin. That's right. Kill the V source, it's a short circuit. Kill the current source, that's an open circuit. What is the impedance seen at the port where ZL was connected? Well, that impedance is negative J10 in parallel with 80, and that in series with 40 in parallel with 40, and that in series with J20. Use your calculator, and the Z Thevenin is 21 plus J10 ohms approximately. That means that our ZL should have as a value the conjugate of that one. The value of ZL should be 21.23 ohms, negative J1015 ohms. We insert that optimal impedance there, solve the circuit, and find the power in that impedance. That's what we're going to do to find what is the maximum power in that source. Reference node, node 1, node 2, and node 3. By the way, instead of solving the one on the top as node 4, which you could, but then I would have to find the current through the 60 volt source. No. I will say that the node at the top has a voltage that depends on V2. That voltage is V2 minus 60 volts. Isn't that correct? Right. And then I will treat the entire V source, the entire evil branch, as a supernode. Those are the branch currents that I have chosen, and then I treat this as a supernode. Supernode, that's right. I'm going to write a KCL equation for that entire yellow zone, this supernode. Let's write the equations. Here we go. That is the equation for V2 minus 60 minus V3 divided by 40. That is the current on the left. I'm writing KCL3. That is equal to the currents leaving node 3. That is V3 over J20 here at the bottom. And then to the right, V3 minus V2 over 40. That is our repeat KCL3. And this one, that is the KCL equation for the supernode. Observe that the supernode has 1, 2, 3, 4, and 5 currents. That's correct. 2 currents going in, V3 minus V2 over 40, and 5 amps. And all the other 3 currents are leaving the supernode. I invite you to check them carefully. And here is KCL1. Find 3 equations, 3 unknowns, V1, V2, and V3. Solve them, and you get V1 is 64.6 with 27 degrees. You say, what about the others? I do not care about the others. I only need V1, which is the voltage on ZL, on ZL, and I can use that expression. The complex power in that impedance is the RMS value of the voltage, 64.6 squared, divided by the complex conjugate of ZL, and that gives me the active power absorbed by ZL and the reactive power absorbed by ZL. Optimum one, because we have chosen ZL to be the conjugate of the Thevenin impedance. Those values, 160 watts and negative 77 VARs. And that is the answer to that question. Now let's talk a little bit about phasors and power. Another exercise, another one, different. Taken also from the Alexander and Sadiku textbook. We have 3 loads. They are specified in different manners, and we have one source that is feeding them all. 200 volts RMS in 90 degrees. Observe that current in the source I sub naught. The question is, find the total P and Q supplied by the source and find the current and the source I sub naught. Well, that is a simple question. You and I remember that we can add all the powers, the complex powers in a circuit as vectors. Yeah, so that's what I'm going to do. The total power supplied by the source will be the sum of all the 3 complex powers. The first one is magnitude 2 kVA, and the angle is the arccosine of 0.707. Why negative? Because it's leading, it's a capacitive load. That's why I've chosen that angle to be negative. And the other one, I add a 1.2 kilowatts minus J 0.8 kilowatts. Why negative? Because that load is capacitive. That's why. And the third one has a magnitude that is P divided by the power factor, 4 kilos divided by 0.9. And the angle is the arccosine of 0.9, positive because it's lagging. It is an inductive load. We add them together and we get that the total power of the loads, which is, according to Telegen's theorem, equal to the total power supplied by the source, is 6.6 kilowatts with negative, oh, there is a J missing there, right? Negative J, 0.28 kilovars. And to find the current, we remember that if we know the complex power actually is the voltage, 200 with 90 degrees, multiplied by the conjugate of the current. We can solve for the current from that equation. We say the current is the conjugate of the complex power divided by the conjugate of the voltage. And again, I missed the J there. I gotta fix those lights. 6.6 kilowatts plus a J, 0.28 kilovars, divided by the conjugate of the voltage, 200 with negative 90. And that gives us that the current in the source is 33 amps with 92 degrees. That answers that question. About phasors and second order circuits, RLC circuits, right? Well, most of you have seen old final exams of mine, and you know that I have some proclivity for choosing these kinds of exercise. I really like them. So they explore many concepts in the arsenal of skills of the student. In this case, instead of repeating what I have already done, let me refer you to existing videos from last year's final exam. There was a question that combined phasors, sinusoidal sources, and a second order circuit. It had two parts. The first part of the solution is on that video there, and the second part of the question can be seen in this other video over here. Please go there and watch. But we're not done. Let's talk about phasors and ideal transformers. That's right, with this exercise. One ideal transformer with a ratio 3 to 1, and a source and 3 impedances, 10 ohms, J 0.2 ohms and 5 ohms. We need to solve that circuit. Fine, let's solve that. Reference V1, but the voltage on the left is not really independent. I'm not going to give it another name. I will not call the one on the left V2. No, we know that according to the ideal transformer, the voltage on the left node is going to be 3 times V1. There is more. An ideal transformer has 2 currents, one for voltages and one for currents. The voltage on the left is 3 times the voltage on the right, and then the current on the right is 3 times the current on the left. Currents entering the dot on one side, currents leaving the dot on the other side. That is a convention. What else? Well, the current on the left, I'll give it a name. It's an unknown. I obey. But then that current I have drawn entering the dot on the left on the high side. That means that the current will be leaving the dot on the right with a value of 3 times I sub B. There, we have only 2 unknowns there. Not 3 or 4. What else? M&A. Now, branch currents, I've chosen them, and then we write the equations. Let me write that equation. The first equation on the left, 100 minus 3V1 divided by 10 currents going in. That is equal to I sub A plus 3V1 minus V1 divided by J 0.2. That is a current on the top. And the other equation is on the right. That is a current at the top. That is equal to that current plus 3IA, that is also entering the node, is equal to V1 over 5. 2 equations, 2 unknowns, V1 and I sub A. Solve them, and we get that V sub 1 is 1.5 volts with 86 degrees, and that the current is 5 amps with 180 degrees. That is the solution. Let's do another one for good measure. This is even more interesting, right? Because it's connected in a very weird fashion. The primary is connected up there on the top, and the secondary is connected on the right. The high voltage side is the one with the 3. The low voltage side is the one with the 1. The ratio is 3 to 1. All right. So let's solve that circuit. We remember that the voltage high is 3 times the voltage in the low side in this transformer, but the current on the low side is 3 times the current on the high side, and if the current is entering a dot on one side, the current is leaving the dot on the other side. Let's see how we can relate them. Reference node, and this would be V1, right? Well, V1 is the voltage on the low side. That means that the voltage on the high side is going to be 3 times V1. And that's right, but we are not there yet. Let's call this node V2. Another node. Fine. Well, observe that to that V2 we have to add the voltage in the high voltage side of the transformer, and we get that the voltage on that node is V2 plus 3 times V1. That's correct. So we have incorporated one of the equations of the ideal transformer, the voltage equation. V high is 3 times V low. Well, that's fine. But now we have to include the currents. This current is isob A, entering the dot of the winding. So this current is leaving the dot of the other winding, and it's 3 times that big, 3 times isob A. And now we represent the branch currents arbitrarily chosen, and we write KCL equations, right? This one, yeah, for this node, the V2 plus 3V1 node, currents entering that node, 100 minus V2 plus 3V1 divided by 10, that is equal to IA. And this other one, the one in the center, isob A, that is equal to V2 divided by this impedance in the middle, 5 negative J2, plus the current on the right, V2 minus V1 over 5. Fine. And then one more equation for the node V1. V2 minus V1 over 5 plus 3 times IA, that is drawn entering to, that is equal to 0. We solve them, and we get isob A is 1.3 amps with 6 degrees. V1, that is 27 volts approximately with 0.4 degrees. And V2, there is a typo there, that should have been V2. That's what I win from cutting and pasting and replacing numbers, right? V2 is 7 volts with negative 16 degrees approximately. And that's all. Thank you very much, and I wish you the best of lucks in your coming final exam.